All right, let's talk about mass percent. If you look at a molecular formula, you could ask yourself the question as to how much mass does each one of the individual elements contributes to the overall mass of the compound. And in essence, we kind of have done that in the past by figuring out the molar mass of the compound. And to some degree, we're going to do the same thing again, except that this time around, we're going to look at it from the point of view of percentages. We're going to see how much mass there is for each element in terms of a percentage value. So the way you basically do this, I'm going to start with C6H12O6, is that we find the mass of each element, right? So you look at the periodic table to find the atomic mass of carbon, hydrogen, and oxygen, and you multiply them by the individual values, right? So you have the 6 moles of carbon, the 12 moles of hydrogen, 6 moles of oxygen. And as I said, you look up the um, atomic masses of the three elements in question, and you simply multiply them by each other. So this is no different than what we did before to find the individual masses. All right. This time, you definitely want to write down the masses, though. So the 72.07 for carbon, the 12.1 for hydrogen, the 90.94 for oxygen, and then you add them together. So pretty much what we're doing right here is no different than finding out the molar mass of C6H12O6. That's pretty much what you're doing. Find out the molar mass of the compound. But in addition to that, you're going to have to keep track and you're going to have to record the individual masses of carbon, hydrogen, and oxygen. And the reason why is because to determine the percentage, what you're going to do is divide the individual mass of each element by the total mass. In other words, elemental mass divided by molecular mass. And at that point, you multiply each one of them by 100. So you have your 72.07 grams of carbon divided by the 180.11, which is the total mass. And you do the same thing for hydrogen. You do the same thing for oxygen, except that you use the corresponding values. And then you multiply by 100% to get you 40.01, 6.72, and 53.3 percentages for each one of them. All right, let's do one more example. K2MO2ClO8. We are going to account for the fact that we have 2 potassiums, 2 molybdenums, and 8 chlorines. Now looking up at the masses in the periodic table, right, so we have the following fractions, and if you look at the periodic table, here they are, 39.10, 95.95, and 35.45 for chlorine. So we input those values here to get the individual masses, right? So in other words, find out the individual masses the same way we did as to find out the molecular mass of the compound. And speaking of which, don't forget to add up the individual values with each other to get the total amount, the molar mass. And at this point, you're going to divide each one of the individual values by the total. So 78.2 grams potassium divided by 552.9 grams. The 191.1 grams of molybdenum divided by 552.9. The 283.6 grams of chlorine divided by 552.9 grams. And then multiply by 100 to find out the values. Oh, also, one more thing to be said is that when you get the percentages, if you were to add them together, they should come out to be 100%. And if they're not 100%, at the very least, they should be very close. And by very close, I mean no more than 0.02 percentage points away. So 99.8 is as far as you could get. In fact, even then, it's looking kind of iffy. But if you get 95%, something's missing. You're missing an element. If you got 98%, something's missing. That's too much of a change. So it's got to be very close, like very, very close to 100. All right, now that's the way we go about finding percentages. And of course, you have the formula to begin with, so you can derive the percentages. But what if we didn't have the formula? What can we do? Well, in the case where you don't have the formula, what you're going to have to be given is the percentage value itself. And so what we're going to do is use the percentages and we're going to work our way backwards. And this is something known as empirical formulas. All right, so let me show you how this works out. Let's say that we have this orange compound that has a composition of 17.5% sodium, 39.7% chromium, and 42.8% oxygen. If you add up the values, you're going to find out that they come out being very close to 100%. So this works out. That tells us that all three of these elements are the only elements present in the molecule. But we're going to find out its formula. And notice that right now I'm calling it empirical. There's a reason for that. I'm going to address it a little later. But let's go through the procedure of going from the percentage back to a molecular formula. First, what you're going to do is run under the assumption that you have 100 grams of substance. Now, the reason why is because it will make the math simpler. In essence, if you add up the percentages will be overall 100%. So if you have 100 grams of substance, then by default, all you have to do now is say that the percentage automatically becomes grams, because if you add up all of the grams, they're going to give you 100 grams altogether. So that's kind of like the beauty of the math right here. So we're assuming that we have 100 grams. We don't actually have to have 100 grams, by the way, but because of the laws of definite proportion, we are guaranteed that even though with the assumption that we could have 100 grams, even though we may not have 100 grams, we're going to get the same result. So we're just basically tweaking the maths to make the process a lot simpler. So take that percentage sign, turn it into grams automatically. And now what we're going to do is we're going to find out the moles of each individual element. So we need to look at the periodic table, look at the atomic masses, 22.99 for sodium, 51.99 for chromium, and 15.99 for oxygen. And just remember the units are grams per mole. So whatever the number, or excuse me, wherever the grams go, that's where the number needs to go, right? So the 15.99 grams of oxygen have to go on the bottom so that they cancel out with the grams of oxygen. In the opposite end, we have the 1 mole. Number on the bottom, 1 mole on top. Number on the bottom, 1 mole on top. All right, so this will give you the moles of sodium, the moles of chromium, the moles of oxygen. And since you're going to have to do this for a number of elements, I recommend that you use at least 4 decimal places for your answer. You might even use a little bit more. Now here I'm getting a little bit more cavalier, right? Because I'm only using 3. But I would recommend that you use 4 decimal places. Disregard the sig fix at this point. The reason I'm asking you for that is because you need to see some changes and you need to um, introduce enough precision into this calculation. All right, now what ends up happening is that because we are basing the premise, no, this entire problem on the fact that we have 100 grams, and we are assuming that the individual masses add up to a whole, you could say, well, in terms of moles, we know that we're going to have an X number of sodiums, chromiums, and oxygens in 1 mole of the molecule. We don't know exactly how many moles of molecule we have, but we do know that the proportions in terms of the atoms themselves, like sodium based on chromium and chromium based on oxygen, etc., they have to be roughly whole numbers. So what we end up doing is we divide each one of these moles by the lowest value, because doing that will ensure that you end up with values that are greater than 1. And ideally, they should give you values that are whole numbers. Now, if you actually carry out the division, right, in this case, the smallest value is sodium, 0.7612 out of all 3 here. So if you divide each one of them by 0.7612, you're going to find out that you have 1 sodium, 1 chromium, and interestingly enough, 3.5 oxygens. All right, now in the case where you end up with a decimal number that really can be round up or round down, and by the way, what I mean, at least on paper, for you to be able to round up or down a value, is that the number should be no farther than maybe point. I'll go as far as to saying zero point 0.2, but even that's kind of crazy. So plus or minus 0.1 is probably where you want to go in terms of rounding up and rounding down. If you have more than that, then you're going to have to basically multiply the entire set of numbers by whatever makes this decimal go away. And zero point 0.5, if you multiply by 2, zero point 0.5 turns into 1. So that tells us that we want to multiply each one of these values by 2, such that the 3.5 becomes 7, which is a whole number. But this needs to be applied to all 3 of the elements. Now, the moment that you end up with whole numbers for all the elements, you basically write them all out. This tells you that the formula should have 2 sodiums, 2 chromiums, and 7 oxygens. So the formula is probably Na2Cr2O7, also known as sodium dichromate. All right, so that's the empirical formula. Now let me show you one step further, known as the molecular formulas. Now the reason that this could differ is because we don't necessarily know if the empirical formula may be equal to the molecular formula, because it turns out that the empirical formula is going to always be the lowest ratio in terms of the subscripts. And sometimes the molecular formula may have values that could be lower down to a lower ratio, but you don't want to do that because you want to have that specific number of atoms. So let me show you an example of that. Let's say that we now have 65.44% of carbon, right? We have now 5.19% for hydrogen, 29.06 for oxygen. We want to find out the molecular formula ultimately. And now notice that we're given the molar mass of the molecule itself. So this is something we didn't have in the previous example, but now we do. And we need to have that in order to find out the molecular formula. So I'm going to run down through the procedure once more. We have 65.44 grams of carbon, 5.49 grams of hydrogen, 29.06 grams of oxygen. Literally change the percentages to grams. Now convert to moles. Looking at the table, you use the atomic masses 1.008, 12.01, and 15.99. And you divide each of the individual masses by the corresponding atomic mass. That will switch you over to moles. Write down the values. I would still recommend that you go up to 4 decimal places, even though I'm only using 3 in this example. And at the end, divide each one of them by the lowest number. In this case, the lowest number is 1.817. So you divide each of those values by 1.817. And in this case, you're going to find out that you get values very close to 3 for carbon and hydrogen, pretty much 1 for oxygen, since that's the smallest value. And since you don't have any decimals, you don't have to worry about multiplication. So now you can just write the empirical formula as C3H3O. All right, now here's where we're going to start looking at the molecular mass. First, we need to find out what the overall molecular mass, technically the empirical mass of this formula is. So we're going to find that out. We have 3 carbons, we have 3 hydrogens, we have 1 oxygen. We multiply each one of those numbers by the atomic mass of the elements, and then we add them up together to give us the empirical mass, which is 55.04 grams per mole, technically speaking. All right, now let's compare that to the molecular mass. Specifically, let's divide the molecular mass by the empirical mass. So we have 110 and 55.04. Needless to say, the two numbers are not the same, but the ratio of them tells us that we are off by basically a factor of 2. So all that you need to do now is take the subscripts in your formula and multiply them by 2. So that means that you will have now 6 carbons, 6 hydrogens, and 2 oxygens. And this is the true molecular formula of the compound. All right, now I'm going to show you a shortcut for the molecular formula. This only works if you do have the molecular mass given. If the molecular mass is not given, you will not be able to do this. But here we go. We have basically, it's the same problem, identical, but I'm going to show you a different way of looking at it. And the way we do this is by, instead of running under the assumption that we have 100 grams, we're now going to go under the assumption that we have the same amount of mass as the molar mass of the compound. And by doing so, right, selecting the 110 grams of this substance, we are ensuring that we're dealing exactly with 1 mole of the molecule. All right, so because this is based on 1 mole of molecule, now what we can do is say, well, okay, the 110 grams is the mass of the entire thing. But we know that there is 65.44% carbon, 5.49% hydrogen, 29.06% oxygen. So multiply the mass of the entire compound by 65.44 divided by 100. What that will do is give you the mass of just the carbon present in 1 mole of the compound. Multiply the 110 by 5.49 divided by 100. That will give you the mass of just the hydrogen present in 1 mole of the molecule. And 110 multiplied by 29.06 divided by 100 will give you the mass of just the oxygen. So at that point, all you need to do is change the masses of carbon, hydrogen, and oxygen to moles. So you divide each one of these masses by the atomic mass of the elements. And the moment you do that, in these 3 steps, or technically 2 steps, boom, the value you get is 6 moles of carbon, 6 moles of hydrogen, 2 moles of oxygen. You have automatically gotten the molecular formula of the compound. So I personally love the shortcut. I mean, it gets to the point, it gets you the value, you don't have to do like all the extra fluff. And at the end, if you need to still say or mention the empirical formula, all you have to do is divide the values that you see in the molecular formula to the lowest ratio, and that will give you the empirical formula. All right. I'm going to do one more example to show you the process, and at that point we'll finish with this video. All right, so the empirical formula, we're going to find out the empirical molecular formulas of resorcinol, and we have the values for carbon, hydrogen, nitrogen, and oxygen in terms of percentages, and we're given the molecular mass. So I'm going to do it the long way first, and then I'll show you the shortcut. All right, so we're going to start with the percentages. Turn all the percentages to grams. Change the grams to moles using the atomic masses of the four elements. Okay, so divide by the atomic masses. Get the number of moles. I would recommend 4 decimal places. Divide each one of the moles by the lowest amount, which in this case is the 1.03 moles of oxygen. So everything is divided by 1.03. This will give you actually whole numbers: 4 for carbon, 5 for hydrogen, 2 for nitrogen, 1 for oxygen. So that's your empirical formula, C4H5N2O. Now we find out the mass of this entire empirical formula. So we multiply the 4 moles of carbon, the 5 moles of hydrogen, the 2 moles of nitrogen, and the 1 mole of oxygen by the corresponding atomic masses. And then we add them together to get the empirical mass. At this point, we notice that the molecular and empirical masses are not equal to each other, so we divide the molecular by the empirical mass. And then what ends up happening is that 197 divided by 97, or 195 divided by 97 equals 2 once again. So this tells you that the entire formula here needs to be multiplied by 2, meaning that you actually have 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. All right, so that's the long way of doing it. Let's see how the process gets done if you do it the short way. All right, so all you need to do is say, okay, we have carbon, hydrogen, nitrogen, oxygen, 4 different elements. So we write the molar mass 4 times. And then what we do is we multiply by the corresponding percentage divided by 100. All right, so 49.5 over 100, 5.15 divided by 100, 28.5 or 28.9 divided by 100, and 16.5 divided by 100. Then divide by the corresponding atomic mass. Carbon is the first one, hydrogen is the next one, nitrogen is the next one, and oxygen is the last one. So just make sure you don't forget which one is which, otherwise that could present problems. But you divide by the corresponding atomic masses, and the value you get directly from this calculation, 8 moles of carbon, 10 moles of hydrogen, 4 moles of nitrogen, 2 moles of oxygen, is automatically the molecular formula. So as you can see, that's a lot more mellow than what we did in the previous slides. And of course, if you want to get the empirical formula, divide this by the lowest ratio to get to 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen. That will be the empirical formula. All right, so this concludes the empirical molecular formula portion of this lecture. In the next video, I'm going to talk about combustion analysis.